first video in this series looked at the original Richter magnitude of earthquakes, which is based on the maximum horizontal displacement of the ground. Now we focus on another factor which is even more important in assessing the danger of earthquakes, a factor directly linked to Newton's second law. To demonstrate our point, we will design a magnitude 4 earthquake which causes more damage than a magnitude 5 quake. Modern seismologists and geophysicists use several different magnitude scales, but all have been adjusted to give similar values to the original Richter scale, at least for weak to moderate earthquakes. Magnitude 3 generally represents the weakest quakes which ordinary people might notice, and the 100 times greater amplitude of a magnitude 5 quake is roughly the threshold above which there is likely to be some damage to vulnerable structures such as chimneys, items on the shelf of a grocery, or a shoddily constructed building. As Galileo and Newton recognized, the accelerations we experience make a difference in ways that position and velocity do not. Displacement can cause significant damage directly, for example if one part of a water pipe moves west while another part of that same pipe moves east, but most earthquake damage is much more directly related to acceleration. Earthquake hazard maps produced by the U.S. Geological Survey are based on acceleration, and these provide the primary basis for the building codes which guide architects and engineers as they design buildings, dams, bridges, pipelines, and other structures in earthquake-prone areas. In our simulations, we use a stack of 25 pennies to represent a shoddily constructed building, and we take an amplitude of 1/10 of a millimeter to represent a barely felt magnitude 3 earthquake. We can simulate earthquakes up to about magnitude 5 with an amplitude of 10 millimeters. We can replicate actual seismic data, or we can design our own earthquakes using algebraic functions. In later videos, we will look at ways to make our structures more earthquake resistant, perhaps using different building materials, different geometric structures, or different foundations. For now, we will stick with a simple stack of pennies on an anti-slip foundation as we try to design a very low magnitude quake which can still topple Pooh onto his nose. Our first test uses one-dimensional data recorded during a 7.1 magnitude quake which occurred in Alaska in 2016. The quake was felt across much of the state and caused minor damage to some homes. We've scaled the motion down so the maximum displacement is 10 millimeters, corresponding to a magnitude 5 quake, but we've kept the shape of the motion unchanged. The greatest accelerations occur about 15 seconds into this 60-second earthquake, when the velocity jumps quickly from about plus 40 millimeters per second to about minus 40 millimeters per second. Pooh would certainly notice the shaking, but he seems safe and the pile of pennies seems undamaged. We can try data from other earthquakes, such as one related to volcanic activity in Hawaii in 2006, but in our effort to knock Pooh off his perch, let's jump straight to one of the biggest magnitude quakes ever recorded, a magnitude 8.8 earthquake which occurred off the coast of Chile in 2010. Since we are looking at the nature of the vibrations, not the amplitude, we again scale this quake back to have a maximum amplitude of 10 millimeters, corresponding to a magnitude 5 quake. There are a good number of rapid changes in velocity, again shifting rapidly from about plus 40 to negative 40 millimeters per second, and this quake continues for over 2 minutes. Even 2 minutes of shaking, however, caused no noticeable damage to the pile of pennies. Let's try one more set of actual earthquake data, this time from a 5.1 magnitude earthquake in Oklahoma in 2016. We had an extra jump as the earthquake simulator reset in preparation for the motion, and that caused clear damage to the pile. In fairness to Pooh, we ought to repair that damage before continuing, but I'm anxious to see a collapse, so we'll test the impact of this magnitude 5 quake on a previously damaged and shoddily constructed pile of pennies. The shape of the motion also looks particularly dangerous, with many rapid swings in velocity between about plus 60 and minus 75 millimeters per second. Building inspectors would probably insist that this structure be evacuated, but even using a magnitude 5 set of quakes, we have not yet managed to really bring about a collapse. Is there any hope at all of making a collapse of the magnitude 4 quake that is just 1/10 as much displacement? The Math Machine software offers some standard periodic functions, and it seems worth trying at least one of those to see if even a magnitude 5 earthquake can knock over this pile of pennies. We could try the ever popular sine wave, but that has particularly low velocities and rather gradually changes in velocity. A sawtooth wave might be a better bet, with a slow motion in one direction and a very rapid, as fast as the motor will allow, in the opposite direction. Having failed completely in our attempts to knock over the pile of pennies of the magnitude 5 earthquake, we're still going to take a shot at doing it with a magnitude 4 quake. We've designed a piecewise defined algebraic function that begins with a slow displacement to the extreme negative position, then begins a periodic motion built about the absolute value of a cosine function. The idea is to have gradual accelerations in the positive direction combined with the most extreme possible negative acceleration at the point at which the building reaches its most positive displacement. Notice that the amplitude of the vibration is just 1 millimeter, corresponding to a magnitude 4 earthquake. Okay, that doesn't seem to be working either, but maybe we just made a mistake with a decimal point. What if we change the period of the vibration from 20 seconds to 0.20 seconds? That does increase the maximum velocity and decreases the time per cycle, and it also lets us fit more vibrations into the 30 seconds we've allotted ourselves. I think that deserves a replay from another camera angle. Maybe acceleration really is more important than displacement.